Okay, I'm going to start off with, I named this history of science. Really, it's the history of the development of the atomic model. I need to throw something. Look at this. This any way to run a school? All right. So anyway, and then we're going to end with the current atomic model, which is the quantum mechanical model. And then we're going to talk about the periodic table as well today. Okay. Now, what I want you to get from this history of science presentation is, one, how the model developed. And we're going to go through certain parts. For example, who discovered the nucleus? Who discovered electrons? What were the models that they used to describe it? And this started thousands of years ago, long time ago. One other thing, by the way, a lot of people, particularly in an introductory science class, don't know what science is. And a lot of people think it's the truth. It's not the truth. It's an attempt at describing what the observations are. And if the observations change, well, then the quote unquote description or the truth changes, but it's not an absolute truth. A lot of people quote stuff. They go, well, the Earth's flat, or we didn't land on the moon, and all this stuff. So anyway, bottom line is things change. As you walk around the museum here, you'll notice a lot of fossils. Well, when you find a new fossil, the fossil either is consistent with the current model or it's not consistent. If it's not consistent, then you might want to look at looking at the model itself and possibly changing it to fit the new data. So as we gather data, the model is in flux, 24/7, 365. That's what science is. Additionally, in modern science in Western countries, there has to be an acknowledgement that what you did is real. Like, say you come up with something. Right now we've discovered elements out to 118. Say you think you came up with something at 120, but no one's able to reproduce what you've done, well, then it isn't valid in the scientific community. That's what current science is about. If you find something or do something, it has to be reproducible. If it's not accepted. I'm going to talk about alchemy in a little while. And that's one of the big issues with alchemy, is it doesn't work for a number of reasons I'm going to talk about. Okay. All right. Okay. So let's talk about the Greeks. There are two major schools of thought at that time. A guy named Democritus and a guy named Aristotle. You've probably heard of Aristotle, but possibly not Democritus. Aristotle thought all matter is composed of four elements. It's not earth, wind, and fire. Earth, air, fire, water. And he was a very popular philosopher, and his work stood the ages of time. Thousands of years, people believed in that. But the other school of thought is a guy named Democritus. He believed that there is small bits that determine what something macro is. Stapler. Okay, if I cut this stapler in half, is it still a stapler? Probably not, but it kind of looks like one, depending how you cut it. Well, his idea was if we keep cutting this down, smaller and smaller and smaller and smaller, smaller, it's like taking a set of Ginsu knives and at one point, it stops being a stapler. That's the point. He said, we've reached something called no cut. And in Greek, that is atomos. And that's where the word atom comes from Democritus. Okay, so don't write all this down. Write down Democritus, atom. Aristotle, earth, air, fire, water. No more than that. And this is a PowerPoint available, should be available as well in files, Unit 2. Okay. In Western Europe, mostly, and when I say Western Europe, it's most all of Europe, but when you get towards the Mongolian area of Asia, things are different. The age of alchemy started up. And alchemy is a way when people started doing things that appeared to be magic, the alchemists explained them, where before that, there was no explanation at all. So, and of course, every king wanted a set of alchemists because they were trying to take cheaper metals like tin and lead into gold. And so that's what kind of funded the alchemists. And so they had to put a certain amount of energy into that. But really what they were trying to do is they were looking for the elixir of life. And they did a lot of, experiments, quote unquote, and stuff to impress the king. There were two main problems with alchemy, though. They didn't use a standard method to do their experiments, in which case other people could not repeat what they've done. The other problem is the language for which they use to explain it was not common. For example, and think about the 1400s in Europe. You had Paris, which was basically a big village. You had London, another big village. Stockholm, those giant cities that we have now were villages in those days. And to contact someone in the next village over, you did it two ways. You had walking or you had a horseback. And so communication from village to village was poor in those days, to say the least. So if someone, quote unquote, found something out, they could not share it very well because both the language and the communication was very poor. What I mean by language is, like in lab today, you're gonna be using a beaker. Well, a beaker in London is not called a beaker. A beaker in Paris is not called a beaker, it's something else. So they had an uncommon standardization on their language they used as well. So there's a lot of stuff going on which made alchemy kind of hard to do much with. But it was the birth of modern physics and chemistry. Now, a lot of textbooks, particularly, pay no homage to other cultures regarding science. And two good examples is the Middle East and China. They were doing stuff way before Europe was, way before Europe. And particularly Middle East, they were not given any credit for doing any of these early stuff. We're talking 9th century. This is really a long time ago. Anyway, my point is that this modern chemistry did not evolve from just Europe. It evolved from the whole world. Okay. So a guy named Dalton came along, and he was the first kind of modern perspective on science. He also dispelled Aristotle's idea of the atom. They went to Democritus' idea of the atom, the no-cut version. Okay, so his atomic theory. 5 parts. Matter is composed of indivisible particles, atoms. Atoms of a particular element are identical. So I have a piece of gold, and all the atoms inside the gold are gold. They're not something else. Some of these are like, duh. Different elements have different atoms. So silver atoms aren't the same as gold atoms. Patience. Atoms combine in certain whole number ratios. What's the formula for water? H2O. 2, it's not 1.999, it's exactly 2. It's not 2.111, exactly 2. That's what that's talking about. And number 5 is not true today. I think I'm going to go to the dean next. I know her really well, and she's all for technology. Okay, so it says they are not created, destroyed, or changed in atoms in any way. In other words, if you start with 5 atoms, you end with 5 atoms. Most of the time that's true, but there's something called nuclear chemistry that changes that. Things are transformed in nuclear chemistry. Not only that, atoms are transformed to other kinds of atoms in nuclear chemistry. Atoms that are unstable go to more stable versions of that atom. Yeah. Say again? I think I heard part of that. Yes, they can be changed, number one, and they can be converted to energy as well. So there's an interconversion between matter and energy. You've all heard M is equal to MC squared. That's the conversion process. So number 5 is in common chemistry true, but it's not all the way true. Okay. And remember, I've got a copy of this. You don't have to take extensive notes, okay? All right. Number 1, normally we can divide it down to the atom. Any further than that, we create lots of energy. And he didn't account for isotopes. And then number 5 is it doesn't account for nuclear reactions. Okay, so it was a really good start. Dalton is a very important person in modern science. Now, at that time, they really didn't, assuming they accepted the atom concept, they didn't know what was going on with the atom, though. So this guy named Thomson came up with 2 ideas. One is that there's an inherent charge inside the atom that was negative. And he was able to postulate that that charge was not only negative, but different in each different type of atom. So in other words, helium is different than gold, the number of charges inside the atom. And they were negative. So he came up with the concept of the electron. Okay, so Thomson, electron. That's what you need to write down. Number two, he proposed the idea of what's the organization inside that atom. And he said there really isn't any organization. He's just kind of plopped in there. And he used the metaphor of a plum pudding. And plum pudding's got globs in it, or like tapioca. So, but they call it the plum pudding model. So, plum pudding model, electrons. Now, the other thing he kind of discovered was the atom itself was neutral. Yet he was able to discover these negative particles in there. If the atom's neutral, that means there was something there that was opposite the negativity. So he sort of discovered protons, which are positively charged. But he didn't have any proof, where he had much more proof of the electrons. So he just mentioned it. He says there's got to be something to counteract that charge. And later they came up with the concept of a proton. In fact, he called electrons early on corpuscles. And this talks about how atoms or protons came to be. Okay. A guy named Millikan determined the actual charge of the electron. And it's measured in something called coulombs. Now, charge is interesting because a proton's positive charge is exactly equal to the electron's negative charge. So they're equal but opposite. So Millikan, charge of the electron. Now, the scientists are starting to get into the form of replicating someone else's model to verify that their thinking was consistent with the data at the time. A guy named Rutherford came along, and he was known to be, he got a Nobel Prize, not in this though, in some nuclear chemistry stuff. He was also a physicist, not a chemist. Okay, this is an experiment he devised to test the plum pudding model. Now, the thing with the plum pudding model is if you have a billiard ball and you hit it with another billiard ball, does the first billiard ball go away? No, it just bounces around. So what he did is he devised an experiment where he took some gold foil, gold is a very dense atom, and shot it with a ray gun. And the ray gun was an alpha particle. Now, alpha particles are of the radioactive subatomic particles are the biggest. They're basically a helium nucleus. So there's 2 protons, 2 neutrons, big subatomic particle. So he shot it out of this lead box into this little area at the gold foil. Now, with plum pudding's model, all the alpha particles should have been deflected, bounced off, just like in a billiards game. But this is what happened. Most of them went through the gold. Like 99% of them went through the gold. And he was going, how can that be? He had a few deflect off. Most of them went right on through. So plum pudding says that's solid. There's no way any of them should have gone through. All of them should have been deflected. But only 0.1% went through, or even smaller. It's very, 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 very few. So the model now has to be revised because the data is not consistent with the model. Because basically, this is what Rutherford's saying. And don't forget, this is like the early 1800s. I'm standing on nothing. Why do I not go through the floor? I mean, that's even today, if we go out on campus and grab a person walking and explain that we're standing on nothing, they're going to go, you are a fool. It's really hard model to get your head around. But his data supports that. So what he said is the atom is composed of electrons, no organization yet, they're just in there. But most of the space is nothing. And the mass of that atom is contained in a tiny little dot. And let me show you the dimensions of that dot. Let's take a major football game stadium. Big. And you take a marble and put it on the 50-yard line in the middle. So the total mass of that atom is located in that little marble. Everything else is nothing except these electrons buzzing around. So 99.999% of the mass of that atom is in that tiny, tiny little space. Now, you all know what's inside the nucleus, protons and neutrons. What charge are protons? Positive. And what do positive charges next to one another want to do? Cling to one another or, yeah. Excuse me. So you've got these tiny, tiny, tiny charged particles in this tiny, tiny, tiny space. And they're not flying out. So there's a force there keeping them together from flying out. And that's why nuclear energy has the tremendous amount of energy available in it when you start messing with that nuclear force. It's because it's very, very strong. And again, this is the 1800s. Horse-drawn carriages. And they're talking about what? Okay, so Rutherford nucleus. There was a disconnect, though, is on mass. It appeared like we could get different forms of atoms that chemically do the same thing, but they don't weigh the same. And that's what Chadwick came up with, the concept of the neutron. So he says, well, there's some non-charged particles in there that don't interact with the protons and electrons. Actually, when you study nuclear chemistry, a neutron is actually composed of a proton and a neutron, or a proton and an electron together. So electrons can be inside the nucleus as well as outside the nucleus. Okay. Ashton put that together, concept of the neutron, and said, well, we can have carbon 12 and carbon 14. Excuse me. The chemistry of carbon between carbon 12 and carbon 14 is the same, but they don't weigh the same. So those two carbons are considered isotopes. So isotopes differ in the number of neutrons. Chemistry is the same. So Ashton isotopes. Now, Bohr came along, also got a Nobel Prize. He was going, there's got to be some organization for these electrons. They just aren't in there nitty, running around on their own deal. There's got to be some organization. So he proposed with a ton of fancy math that electrons are restricted to certain paths. It's just like the movie Men in Black. Remember what was on Orion's belt? Who saw Men in Black 1? Remember what was on Orion's belt? It was a galaxy. Remember it was wearing it on his collar? It's a galaxy. And the galaxy has got solar systems in it. So Bohr said, how perfect. We're taking a galaxy down to a solar system, down to an atom that could be like planetary orbits. So these electrons are restricted to orbitals. Nowhere, they cannot leave that orbital. There's only a certain number of them that can fit on, because the inner orbitals are small, because they're close to the nucleus. So you can only fit 2 electrons in that. The next one out is a little bigger, so you can fit more electrons on it, 8. And it kept expanding out to 7 sets of orbitals. And lastly, class may end early today. And lastly, an electron is going to reside on the most stable place for it. That's the way the universe rocks. Things go from unstable to stable. So if you have an electron, it's going to reside on its most stable place, which is the closest orbital to the nucleus. However, electrons can move freely from one orbital to the next. However, it requires energy to do that. So when you go from unstable to stable, it gives off energy. When you go from stable to unstable, it requires energy. So this is what he's talking about. So if we're going to go from a stable orbit to an unstable orbit, it's going to require energy. So the energy goes from the ground state, most stable, to an excited state, unstable. And the electron does not want to stay in that unstable state. It wants to come back to the ground state. So when it comes back to the ground state, it gives off energy, the same amount of energy it took to get there. So these fluorescent lights, that projector bulb and that projector up there, all do this. That's how they produce light. Now the energy given off happens to be in the frequency of visible light. That's why we see. But it also gives off energy in the ultraviolet and infrared as well. So those 3 areas: infrared, visible, ultraviolet. Okay, so that's what he won Nobel Prize on, is this little gimmick here. It's how lasers work. Yeah. That's when they give off energy. Yeah. So it takes X amount of energy to get it up, and when it comes back down, it gives off X amount of energy. Exactly the same. However, sometimes it takes a number of deals to come down. So the sum of all of them will be what took to get up there. Okay. Now, there are some issues with the Bohr atom model. Again, this is about 120 years ago. They were saying, Bohr, you got a Nobel Prize for this, but there's some issues that aren't addressed. One is it takes energy for an electron to go on a curved path. Electrons want to go on a straight path. So if it's not supplying energy, that electron will spiral into the nucleus. And that's not what happens. So his model did not answer that question. So they came up with a new model. This is where Einstein comes in, called the quantum model or the quantum mechanical model. And what that is instead of orbitals, he says, statistically, this is where we're going to go to find an electron, not how the electron got there or what the path was to get there. It's just there. Let me give you an analogy. When I go to Rayleigh's, I notice there's a side door on the side of the building, and it's got a whole bunch of cigarette butts on the ground. A whole bunch of cigarette butts on the ground. And I was going like, well, where did they come from? I don't know. But I know where to go to find the cigarette butts on the door on the side of the building. I don't know if those are customer butts or employee butts, but I know where to find them. And that's the essence with a bunch of math. That's the essence of the quantum mechanical model, is we're going to statistically treat where the electrons are going to be at any given time. So it's like a cloud. Now the clouds are similar, some of them are similar to the Bohr model. The clouds kind of simulate a planetary orbital, but not that the electrons go around it, is that they can be found in this area. And outside of these orbitals, the chances of finding an electron is positive, not zero. So anywhere in that space, you can find an electron according to quantum mechanical model. But some areas are more favored than others. Just like I can find a cigarette butt when I'm walking in the main entrance of Rayleigh's. What are the chances of that? Very low, but probability is there. But I know where to find most of them on that side of the building. And that's exactly what quantum mechanics is all about. And that's where we are today, quantum mechanical model. So it's kind of interesting how it evolved. And I want you to note also that the model evolved because the data did not fit the model. So the model had to change, not the data. You can't argue with your data unless you interpreted your data incorrectly. But the model is what changes, not the data. New data, new model. Okay, out here, an extraterrestrial lands. New data. Or we go explore Roswell, the other way to go. So when we get new data, the model changes. And that's kind of where we are. This guy, really cool guy. When I was in graduate school, I went to Davis, and every week we had a graduate student seminar. And someone had to present. And I was in a graduate group that had chemists, weed scientists, enologists, vintners, toxicologists, food chemistry people, all in this. So the seminars are very interesting because the subject matter was really, really different. And he used to come and he was housed out of Berkeley. He used to come and visit our seminars. So I met him a number of times. And this would be in the 70s. So that was quite a bit before he passed, but cool guy, really, really tall. He was like 6'6" or something like that. He participated in the Manhattan Project. Who knows what the Manhattan Project is? Yeah. Yeah, well, it's to make a bomb from a nuclear reactor. The nuclear reactor was discovered quite a while before that. And Einstein wrote a letter to the president saying, Germany's working on this also, hint, hint. And so they created the Manhattan Project. But anyway, he was one of the people involved in it. A big shot guy. Okay. All right. Any questions about the development of the model? Now, I want you to know just a few words from the scientists, like Rutherford nucleus. That's all you need to know. Bohr planetary model system. Just I want to have a feel for that because a lot of times the science is not covered very well. Okay. All right, so I'm going to end this recording.